running?
Mhm.
Okay. So when we talk about writing and balancing chemical equations, first of all, you have to understand what a chemical reaction is. In a chemical reaction, you have two sides that are separated by an arrow. We call that the yield sign. The side of the reactants and the side of the products, okay? The reactants are made of different chemical elements. Those elements are going to be found in the product. We do not create other elements throughout the chemical reaction. What happens in a chemical reaction is that the reactants, the bonds in the reactants are broken. They're gonna switch places and they're gonna rebond, making different other compounds, okay? And those will be your products. But the elements that come in are the same. So if you look here in this reaction here, you have methane, CH4, and you have oxygen gas. Remember, oxygen is one of the diatomic molecules, okay? So you have carbon, hydrogen, and oxygen, your three elements that come in this reaction on the reactant side. On the product side, you have other compounds, but the compounds are made of the same elements, carbon, oxygen, and hydrogen. See, oxygen shows up in two places. So what? It doesn't matter. It's still carbon, hydrogen, and oxygen. We don't create other elements, but those that are given to us in the reactant part, okay? That is the foundation of the law of conservation of mass and the law of conservation of energy, and in the end, the law of conservation of atoms that you're gonna see coming up, okay? So, I'm going to write this reaction on the board here, and we're gonna talk about how to balance. And the next slides that are coming show this balancing process. We're gonna do it by hand on that board, good? So your reactants are methane, CH4, that reacts with O2. Oxygen, when it's by itself, requires a little 2 at the bottom because it is a diatomic molecule. We talked in chapter 2 about the 7 diatomic molecules. You have a slide coming up that puts those diatomic molecules in front of you again. But this is what you see here. Then I have the yield sign, so these are your reactants. And then it goes to make carbon dioxide and water. So what you see here, you see subscripts, right? The subscripts are part of the chemical formulas. You do not have the right to mess with those subscripts, okay? Once you crisscross a charge, once you figure out the formula from the name, and based on charges or whatnot, those subscripts are set in stone. Don't touch them. What else do you see? That you don't have any numbers in front of your reactants and products. And here, yet you have some numbers popping up, okay? That is the difference between a reaction that is not balanced like this, and this is called the skeleton equation, that is not balanced. That means you don't have any numbers in front of your reactants and products, and a reaction that is balanced that has some numbers in front, okay? These numbers that you see here have been added by me when I did the math on the type of atom that I have on each side of the yield sign. So what do I mean by that? The type of atoms and the number of atoms that are on each side of the reaction, on the product and on reactant side, has to be exactly the same. Exactly the same. And to make that happen, a reaction where you don't have the same number of atoms on both sides is called not balanced, or the skeleton equation. To make it happen, we can help us ourselves by putting coefficients number that multiply that reactant or that product to make up for that difference. So how do we do this? There are different ways, but the standard way is to kind of keep an inventory of how many atoms you have on the reactant side, how many atoms you have on the product side, and kind of multiply and see how it works out. So what elements do I have? I have carbon, here I have hydrogen, and I have oxygen. Those are my three elements on the reactant side. And I have carbon, I also have hydrogen, and I also have oxygen on the product side. Now let's take an inventory. How many carbons do I have here? Just one, okay? How many hydrogens do I have on the reactant side before the yield sign? That's the reactant side. I have 4, okay? I'm gonna write it down. How many oxygens do I have? 2, I'm gonna write it down, okay? Now I'm gonna go on this side, on the product side. Now I'm gonna do the same inventory. How many carbons? 1. How many hydrogens? Okay, I have two hydrogens right here. These two, and water. And then how many oxygens? I have two from the carbon dioxide and one more from water, right? 2 plus 1, a total of 3. Okay. So if you look at the situation, you're gonna see that the carbons are, the same number of carbons is the same, the number of carbons is the same on both sides. Then the hydrogen and the on both sides, here you have 4, here you have 2, they're not balanced. So to balance them out, you have to multiply this hydrogen by 2 to get to a 4. Okay, so if I multiply this hydrogen by 2, I'm gonna lead me to a 4, right? 4 on both sides. But where is this hydrogen? It's right here in water. I cannot touch the subscript, so I cannot take these 2 out and put a 4 just because I feel good about it. The only thing you can do is multiply this whole thing by 2. But these 2 applies to hydrogen, but also applies to oxygen. So the moment you put a coefficient in front of a reactant or product, this water and this product in this case, this number, the coefficient, will apply to all the elements in that compound. Okay, so I have 2 times 2 is 4 hydrogens, but I change my oxygen. So I have 2 times 1. Now it's 2. 2 times 1 is 2, right? So now I have a total of 4 oxygens on the reactant side, on the product side. So 2 from here and 2 from here, total of 4 oxygens. So now you take a step back and you double check, okay, what is my situation? 1 carbon, that's still balanced. 4 hydrogens with 4 hydrogens, these are balanced, equal on both sides. And then I have 4 oxygens and 2 oxygens. Where are oxygens here? In this O2. How can I make this become a 4? I multiply it by 2. This coefficient 2 put in front of oxygen will take care of that. I'm going to multiply this by 2 to make it a 4. Now 4 oxygens on both sides, they're done. Okay? So this method is good for beginners or when you have simple reactions. I mean, it works. But if you have a complicated reaction, to write all this down, if you have like 5 or 6 or 8 reactants, elements, and in products, you're gonna have a lot of balancing to do, a lot of things. So what I do, but I have experience, what I do, I take a step back and I'm looking at the reactions and I say, what hits me first? What do I see that is not balanced? And the first time I would probably see is that a 4 for hydrogen and 2 for hydrogen here. And that's why I would put a 2 here to multiply. Remember that this balancing is a back and forth process. You make a move here, then you check again. And sometimes the coefficient that you put might not be the right one. You erase it, you put another one. It's trial and error. There's not a set in stone method that's gonna say, okay, this is the only way to do it. Okay, so back and forth. So I would say, okay, I see the 4 and I see the 2 for hydrogens, so I'm multiplying water by 2. Okay, that checks one. And then I'm gonna go back and see, okay, let me look at oxygen, check it, and fix the oxygen, and then that's about it, right? So it's sometimes you don't have the time to write down every single thing. At the beginning, it's good because until you kind of start seeing it, but as the reaction becomes more and more complicated, becomes too lucrative to do it like that. So let me give you another example that is not in the slides. I just have to come up with it. Okay, so if I take something like this, aluminum sulfate reacts with magnesium hydroxide to make aluminum hydroxide and magnesium sulfate. So it's like a whoa, what is this? I have aluminum, sulfur, oxygen, magnesium on both sides. That's a lot of stuff to track down. But what else do you notice? You notice the polyatomic ions. polyatomic ions can be balanced as a whole, as a unit. So when you see polyatomic ions on both sides of the yield sign, on the reactants and on the product side, balance them as a whole. Okay, and again, the balancing, sometimes you put a coefficient in front of something and then you're gonna have to change it. When you go back and forth, the reaction kind of calls for what's next. So it's a process that kind of pulls itself through. So first thing that I see, if I take a step back, I see that I have 2 aluminums and 1 aluminum here, right? I can say, okay, let me start with that. That's the first thing that gets me. It's the first element. I could start with a polyatomic ions, but let me start with aluminum, just because that's what I see. Now, can I shove a little 2 here at the bottom of aluminum to make it happen? No. Do not add subscripts. Do not put numbers in between your elements just because you want to, because it will make your life easier. We cannot do that. Whatever subscripts we have are because of the charges. Okay, and the format of the polyatomic ions, don't touch them. So what I can do is to put a 2 in front of aluminum hydroxide. Okay, that means 2 aluminums, I fix those. But let me look at the hydroxide now that I touched that. Hydroxide, 2 times 3 is 6 pieces, right? 6 groups OH. Where's my hydroxide here? Right here. I only have 2. How can I go from a 2 to a 6? What do? I have to multiply magnesium hydroxide by 3, right? Can I shove a little 3 in here? No. You cannot put anything in the middle of the formula. It would be easy, right? Change this 2 to a 6 or shove a little 3 in here, but no. So the only thing I can do is to multiply this magnesium hydroxide by 3. 3 times 2 makes 6 OHs, and now I have 3 magnesiums, right? Now let me see what magnesium is doing on the other side. So I'm going back and forth between the reactants and the products. Once you see one thing that is not balanced, start with that. I don't care if it's the first or you see something else, start somewhere where you see a discrepancy. And that's gonna pull you back and forth until you balance. Instead of writing all these things down. My advice. So magnesium, I have 3 pieces here, and I have to fix it here. So I'm gonna put a 3 in front of this magnesium sulfate. So I have 3 magnesium. So aluminum is done, magnesium is done now, OHs are done, if you think about it. So let me see what the situation is with the sulfate, because these 3 goes for magnesium, but goes for the sulfate, for this whole thing. So I have 3 sulfates in this case, and how many sulfates I have here? 3. So it's balanced. So the moment we put coefficients in front of some reactants and product, that reaction becomes balanced if the coefficients are correct. Where you have no coefficient, that means that it's a 1. By default, that's a 1. And the questions that you might have on the quiz or on the test is, if I give you this reaction, I'm gonna say, what is the coefficient missing in front of magnesium hydroxide? And you do the balancing and say it's a 3. That's one type of question. The other question is, the ratio between the coefficients is 1 to 3, 1 to 3 to 2 to 3. That's another way to put it. So the numbers in front of the reactant and product as written in the reaction that's given to you are these. So that's another way to do it. And another question is the sum of all coefficients is 1 plus 3 is 4, plus 2 is 6, plus 3 is 9. Okay, what's the sum of all coefficients? So remember that if you don't have a coefficient, it's always a 1. So when you have to sum it up, it's a 1. Good? Alright. Now, I have one more thing to tell you about balancing. A weird situation when we have to do a little trick. And let's look, I have a slide. Let me pop that slide up for you. You have other examples in the notes. This is all that we've done with other examples. Here. So I'm gonna write this reaction separately. Whatever you have on this slide, I'm gonna lead you to this, but let's write the reaction. C2H6 plus O2 makes water and CO2. All right, here. So questions that I get sometimes is, can I switch the places of the reactants? Like if I wanna write O2 plus C2H6, can I do that? Yes, you can. As long as they belong to the reactant side, you can switch the places. There's no rule that says one has to be first and the other second. Okay? Same thing here. Can I switch the places between CO2 and water? Anytime. As long as you keep them on the product side. Good? So now, let's check, what do you see that it's unbalanced? When you take a step back and you look at this, what pops in your mind? I see 2 carbons and I see 1 carbon. So my first thing is, let's fix that. I'm gonna put a 2 here to make 2 carbons on both sides, okay? Then I take another step back and I wanna say, okay, my next element is hydrogen. I have 6 pieces here and I have 2 pieces here in the water. So basically, to turn this 2 into a 6, I have to multiply by 3. 2 times 3 is 6. I'm gonna multiply this water by 3, right? Now let's take an inventory of the oxygen. On this side I have O2, so 2. And on this I have 3 plus 4, 2 times 2 is 4 here, so I have 3 plus 4 is 7 oxygens. So here I have 2, and here I have 7. Alright, so 2 and 7, so I need to make these 2 a 7. How do you get from a 2 to a 7? By multiplying by 3.5, right? Or by 7 divided by 2. We never use decimals. Okay? So if you wanna use this, so if I put here 7 divided by 2, 7 divided by 2, 7 divided by 2 multiplied by 2 leads you to 7, right? Which is what you need on both sides. That's one way to do it. If you wanna keep fractions. It's not encouraged because the newer tendency in chemistry is to get rid of the fractions. When I was going to school, fractions were perfectly acceptable. Now they say, nah, not so much. So basically they say this, when you have a situation like this, when you have an odd number of oxygens on one side and an O2, an even number here, go for the common denominator. So between the 2 and the 7, the common denominator is 14, right? 7 times 2, 14. So basically you put the whole 7 here, instead of putting like 7 over 2. If you do the math, now 7 times 2 is 14 oxygens, okay? So it's double than what you need. Because of that, you're gonna have to double up every coefficient that you found. So you have an odd number of oxygens and a 2, you write that odd number of the odd number in front of the O2, that doubles up your oxygens, and that means you double up everything else. So here was a 1, turns into a 2. Here this 3 turns into a 6. Here this 2 turns into a 4. Okay? So if you want to keep the fraction, you don't have to double up, like in this example right here. But if you double up the 7, you double up everything else. Good? Okay. So that is a little bit of a balancing situation. Now, I'm going to go to what else can you see in a chemical reaction? So I have to go back. What additional information you can see? Some reactions, all the reactions have to be balanced. That's a given. When you write a chemical reaction, if you leave it not balanced, it's not okay. It has to be balanced out. But sometimes the reaction can give you symbols like these. S, that's the state of matter, indicate the state of matter of the reactants and product. S stands for solid, so this sodium is in a solid form. L is for liquid, water liquid. Liquid is the symbol for something in its pure state. Water in pure state is a liquid. Mercury in its pure state is a liquid. I don't put liquid for solutions, okay? If a substance is dissolved in water, that's not L. That would be aqueous, AQ. So an aqueous solution means sodium hydroxide has been dissolved in water. Originally, sodium hydroxide is a solid. I take it, I dissolve it in water, I stir it, I make a solution of whatever concentration I want, and that is your aqueous. So this is a liquid, but the symbol is not L. This is just for pure substances. This is for solutions that have a solute and water as a solvent. Aqueous, that means the solvent is your water, okay? And then of course, G for gas. Good? Other things that you can see on the reaction. Look at this. On this I have a little delta, a little triangle. A triangle means temperature. So to take calcium carbonate, which is a solid, I have to heat it up at super high temperature, thousands of degrees, to make it decompose, break into calcium oxide, which is a solid, and carbon dioxide, which is a gas. Okay, so on the arrow, if you see stuff on the arrow, you don't have to worry about that into the balancing. You don't have to worry about the symbols of the state of matters into the balancing. That's just additional information. So when you balance, you focus on just the chemical formulas, not the additional information that may come on the arrow or next to each reactant and product. Okay, so the balancing is strictly like the naked equation. So on the arrow, on the yield sign, you may see indication that the temperature is needed. You can see the word heat, you can see the T for temperature, you can see the symbol delta, you can see light. Some reactions happen under light, under UV light. Some reactions need a little bit of things to speed them up. That's called a catalyst. So you're gonna see the word catalyst, or you're gonna see the chemical formula of a catalyst. Whatever you see on the arrow, just remember that it tells you what the reaction needs to happen, the conditions. Other than that, ignore it because it's not going to interfere in your balancing or in your calculations whatsoever. Good? Good with that? All right. All right, guys, so this is the first part, and we are going to talk about other things in the next video.